Oh, ladies and gentlemen, do we have a monster topic tonight? Just a action-packed lesson, and we're going to get into some really good stuff. So we're revisiting this idea of solving exponential equations. We kind of flirted with this a week or so ago when we were using this method of common bases, and it's an awesome method, but it's the equation's got to be tailored just right for that common base idea to work. So we're going to look at a more universal approach today that's going to have a broader approach, and it's going to be using our log properties. So just to kind of stick this in your back pocket, we really do have two methods for solving an exponential equation, one being common bases from a couple weeks ago, and now all of a sudden we're going to look at our log properties. So, and just consider these two examples. The one on the left, you could use common bases on, because what we're going to do is we're going to take this 16 right here and rewrite it as 4 squared. So now all of a sudden you've got the same base on both sides, and you could set the exponent from the left equal to the exponent on the right and solve real nice. Now all of a sudden, now consider this example on the right hand side. No matter how hard we try, we can't, it's really not feasible to try to write 15 in terms of a base 4. So this is a good example of where we're going to use our log properties, and it's going to make our life a lot easier. So really today's lesson hinges on what we call our third log property, or our power property. And it looks like this. If you have the log base b of, we'll say, m raised to the nth power, the question becomes, what are you allowed to do with that exponent? And what we like to say is that exponent transforms into the coefficient. So it would be n times log base b of m. So we're going to take advantage of that power property today as we go through these examples. So in our first example, we've got an exponent of 3. So that's going to transform into my coefficient, 3 times log base 2 of x. Now in this next example, let's take an extra moment here to just rewrite this as a to the 1/2. And again, then that exponent transforms into the coefficient. Now that log has a base of 10. That's called our common log, and that's the one we'll generally be using when we have the freedom to choose. Okay, very similar here in the third one. We've got an exponent of 2x plus 3 that is going to transform into our coefficient. I do want to put parentheses around it because of its binomial nature. So we've got the quantity 2x plus 3 times log base 10 of y. So if you felt decent about rewriting those, then today's really going to be a walk in the park. So we're going to try to solve these exponential equations and round our answers to the nearest tenth when we're all done. And so what I'm going to do, this is a really fun trick, is, ultimately I want to get this exponent down on the ground, so to speak. And I need to introduce a log into this equation. And again, remember, whatever we do to one side, we've got to do to the other side. So if we want to take the log of the left-hand side, that's fine and dandy. We're certainly allowed to do that as long as we follow suit and do the same thing to the other side. Now I'm going to take advantage of our power property and transform this exponent into a coefficient. So we're going to have the quantity x plus 2 times the log of 5 equals the log of 22. And now I'm going to try to solve for x. We do have multiplication right here, so I'm going to divide both sides by the log of 5. I could go to my calculator right now, but I'm going to hold off, and I'm just going to write it as such. So we've canceled, get my pen back here. So we're going to cancel those terms, and we've got x plus 2 equals the log of 22 divided by the log 5. Now, why wouldn't I just put that into my calculator? Well, you could. The problem is it creates an endless stream of decimals, and I really don't feel like writing them all down. So for me, it's just more convenient to write it the way we did. And then last but not least, we'll subtract the 2 over. Okay. Now that I've subtracted the 2 over, we've isolated the x, and now I'm going to go into my calculator. I'm going to type in this entire expression exactly the way it's displayed. You will have to put parentheses around the 22. You'll have to put parentheses around the 5. And then we'll just round that to the nearest tenth. So I think it looks like it's going to be negative. Well, let me give you what I first have here. 0.079 ... Going to the nearest tenth, we could say x is approximately negative 0.1 for our answer. All right, let's look at example number 2. So again, we're going to go ahead and take the log of both sides. Whatever I do to one side, I'm going to follow suit and do it to the other side. And what that allows us to do is use that power property where the exponent transforms into our coefficient. So it's going to be 2x times the log of 6. Let's divide both sides by the log of 6. Such a funny idea to be using all of these logs. So we've got the log of 82 divided by the log of 6. Now, one option I didn't mention, if you want to put that in your calculator, and we said you certainly can, and just store the answer, right? Just store it so you don't lose the accuracy of having all of those decimal values. And then last but not least, we'll divide that by 2. And so all I got to do is plug all of this into my calculator. My calculator is telling me 1.2297 ... So if we round that to the nearest tenth, we can say x is approximately 1.2. Cool beans, huh? Yeah, we got this. We got this. Now we're going to get a little more challenging here. And the key is we want to stress that we're trying to isolate the exponential expression before we're allowed to take the log of both sides. So in this first one, this right here, if you want to shade that in or highlight that somehow, that's what we consider your exponential expression. So we want to isolate that term before we do anything else. So all we've got to do is add an 8 to both sides. And we could say 4 raised to the negative 3x equals 50, okay? At this point, we have successfully isolated that exponential expression, and we'll do what we did in the last 2 examples where we'll just take the log of both sides. And again, we do have the freedom to take the log of any base of both sides. And we have just chosen to use base 10 in all of these. It's kind of our default setting. And the nice thing about it is there's a button on that left-hand side of my calculator that is tailor-made for log base 10. Okay, so we're going to transform that exponent into the coefficient. So we've got negative 3x multiplied by the log of 4 equals the log of 50. And I bet you're in cruise control right now. Let's divide both sides by the log of 4. Okay, and then we'll divide both sides by negative 3. So we've got x equals, let's see, the log of 50 divided by the log of 4, all divided by negative 3. We'll pump that bear into our calculator. And I think what we're going to end up rounding to is a negative 0.9 when we go nearest tenth. And again, the hardest thing for me to show here and share with you is what I'm doing on my calculator. So that's something that we'll rely on our class time for. So, if you're following every step of the way and you're attempting to put these in your calculator, but you're not getting the exact same answers, then by golly, that's something I think we'll be able to take care of real easily in class tomorrow. Okay, let's highlight the exponential expression. This 8 to the x plus 1 power, that's your exponential expression. That's who you're trying to isolate right out of the gate. So what I'm going to do is I'm going to subtract that 10 over to make 54, and then we'll divide the 2 over to make 27, okay? Now we've isolated it. We can go ahead and take the log of both sides. That exponent is going to transform into my coefficient. So we've got the quantity x plus 1 multiplied by the log of 8. We could divide both sides by the log of 8. Like we said, if you do want to type that in, you can. Just make sure you're storing it. And last but not least, we're just going to subtract that 1 over. And going into my calculator here and rounding it to the nearest tenth, we'll say x is approximately 0.6. Now, these are really not bad to check. We haven't really talked about that yet. One thing you could do is, to ensure your accuracy, what you want to do is maybe store, just prior to rounding it to the nearest tenth, store that long decimal you had, and then just substitute that back into the original. if you just substitute the 0.6, okay, you're going to get an answer that's very, very close in this case to 64, but it would be off by a smidge because of the 0.6 not being our exact answer. It's more of a rounded off answer. Okay, now we are going to dive in and flirt with a couple of real quick word problems here. Let's simulate this idea. The population of Bill's Mafia is currently 750,000 and it's growing at a rate of 32.5% per year. So this is going to be some good review of kind of our how to write an exponential function. Usually when we're thinking exponential function, in this case, especially if it's growth, I'm thinking y equals a quantity b raised to the x power. So based on the numbers they've given us here, to write an equation, and the equation is, we'll name it b of t, that models the population of Bill's Mafia, we would start off with our initial population of 750,000. In this case, it's going to be 1 plus 0.325 because the population's growing. And that's all we need for our equation. Now, what today's really about is being able to solve part B. Find the number of years it takes for the population to reach 4 million. Okay, and we're going to round our answer to the nearest hundredth. So t is the unknown. We are solving for t, and we're going to set the equation equal to 4 million. So we're basically replacing this b of t with 4 million. Let's see what this looks like. 4 million equals 750,000, 1.325 raised to the t. Okay, so the first thing I'm going to do is divide both sides by 750,000. So we got 4 million divided by 750,000 equals 1.325 to the t. So just like we did in the previous two examples, we're trying to isolate that exponential expression. And I think that's worth highlighting. This guy right here is what we consider your exponential expression. And we just needed to divide that 750,000 over. And also what's nice is we could maybe simplify that a little bit. We could cross off some zeros here. So it's really 400 over 75. All right, what should we do next? Let's go ahead and take the log of both sides there. So we've got the log of what was on the left side equals the log of what was on the right side. Okay, and it really doesn't matter whether we put that t on the inside or the outside of the parenthesis. Believe it or not, it doesn't matter. And then we'll just say the exponent transforms into the coefficient. Log of 400 divided by 75 equals t times the log of 1.325. And then we'll just divide both sides by that log. So ultimately what we've got here is the log of 400 divided by 75 divided by the log of 1.325 equals t. Going into our calculator and rounding it to the nearest hundredth, I got 5.95 years. And just a word of encouragement to be extra cautious with your rounding. It's usually a time in the problem where we kind of let our guard down and we just kind of take rounding, whether it's the nearest 10th or 100th or 1000th, we kind of take that for granted. And unfortunately, it seems like on the midterm or final exam each year, we lose more points for rounding than anything else. It's really a nightmare scenario to lose points there. We're going to simulate a radioactive isotope, and this one's decaying. Okay, so their value is decreasing at a rate of 4% per year. And originally there were 120 kilograms of this radioactive isotope. So part A, let's see if we can just write an equation that's going to model the amount of radioactive isotope left, t years from now. So we'll say the amount left is equal to the original amount, and then we'll do 1 minus 0.04 raised to the t. Or what we could say 120 times 0.96 raised to the t if you want to clean it up just a smidge. That's always nice. Find the amount of time it takes for only half of the initial amount to remain. So that's like asking them how many years are going to pass before we're down to 60 kilograms, okay? Because 60 is, of course, half of that 120. So let's just set this equation equal to 60. In other words, replace that A of t with a 60. All right. Now, think about your exponential expression here. Your exponential expression is this rascal, and we want to try to isolate that. So we're going to divide both sides by 120. And 60 divided by 120 is a half. We'll go ahead and take the log of both sides. So the log of 1/2 equals the log of 0.96 raised to the t. That power property, where we said at the beginning of the video, today's lesson really hinges on that power property, where we're going to take our exponent, transform it into the coefficient, and we'll divide both sides by the log of 0.96. So very, very methodical, very rhythmic here today. You'll feel yourself kind of following the same process throughout. We'll get into our calculator, and I'm going 3 decimals. Now check this one out. When I plug this into my calculator, I got 16.97974. And we're trying to round to the nearest thousandth, which is going to be 3 decimal places. So you look at the 7, and that tells you to round up. So what does that kick you up to? Let's see, t is going to be approximately 16.980 because of the rounding that took place. Okay, so it's going to take just a whisker under 17 years for that radioactive isotope to decay to half of its original amount. All right, hope you're feeling pretty good, and we're going to get after it tomorrow.